Hello everyone. I am Julie Ann Banato from the Philippines. I would like to share how a developing country like ours jump-started our journey into space, an endeavor that most people think is only reserved for first world countries. I am a member of the Philippine government program to develop our space technology proficiency. 6 years ago, we did not have any space related activities. The government just bought satellite images from commercial providers when disasters such as typhoons struck the Philippines and we needed more data. This changed in 2014 when our Department of Science and Technology decided that it will be much cheaper if we built our own satellites for remote sensing. However, we did not have the necessary expertise to build it locally. This is why we partnered with foreign institutions so that they can provide the necessary guidance. Thus, the Film Microsat project is born. This is a collaboration with Tohoku University and Hokkaido University in Japan. It aimed to build, launch, and effectively utilize microsatellite technology for multispectral, high-precision Earth observation. As a member of PhilMicrosat, I was sent to Tohoku University to build our second microsatellite Iwata 2. My tasks included modeling of the wire harness during the design phase and vibration analysis during the testing phase. The PhilMicrosat program resulted with two microsatellites and one nanosatellite launched into orbit. In parallel with satellite development, I was enrolled as a PhD student in aerospace engineering. I formulated my research to optimize microsatellite operations based on the lessons learned from Diwata 1 and Diwata 2. This led to my PhD thesis, which explored autonomous target pointing, onboard image processing, and attitude control to improve quality of images captured. After the success of our microsatellites, and to consolidate the growing space-related activities, the Philippine Space Agency was established by law in 2019, an amazing feat for a developing country. For now, efforts are concentrated to ensure that space activities spearheaded by the government spill over to academia and the private sector. In conclusion, the Philippines became a spacefaring nation thanks to international collaborations. From this achievement, my fellow Filipino engineers and I strive to take it to the next level, ultimately make us self-sufficient, and have Filipino-made space technology, this time through local partnership.
Hello everyone, my name is Joshua Ingersoll and I'm a spacecraft systems engineer at the Aerospace Corporation. Successful free space optical communication has long been sought after by space community organizations like the Defense Advanced Research Projects Agency, or DARPA, NASA, and countless commercial startups due to its increased security and its revolutionary increases in bandwidth capability. Optical communications replace the traditional radio frequency transmitters and receivers with laser diode emitters that create beams of visible or optical light. This beam is incredibly more focused when compared to RF emissions, but due to the concentration of the energy and the much shorter wavelength of the light, orders of magnitude more information can be stored in the beam. This increase in bandwidth and security makes the technology very lucrative for both commercial and military use. The future is not all sunshine and roses, though. There is one main challenge facing the integration of these optical intersatellite links into future space systems, and that's cost. Currently, due to the economies of scale being seen by manufacturers such as SpaceX and OneWeb, the cost of adding an OISL terminal to a satellite can be more expensive than the rest of the spacecraft combined. This has caused both companies to postpone OISL integration until their second-generation constellations, and has left many prospective OISL vendors without initial customers. To help solve this problem, I worked with OneWeb Satellites on their bid to be the bus provider for DARPA's Blackjack program. by analyzing what types of constellation-level integration strategies of these OISL terminals would provide the most benefit at the lowest cost. This program is doing what public-private partnerships do best, spreading the financial risk and the technological benefits across both the public and private sectors, in this case, DARPA and OneWeb satellites. My analysis tool looked at 4 different integration strategies and found a 47% difference in cost between the cheapest and most expensive, with the cheapest architecture actually providing the highest average bandwidth as well. These results were recently published as part of the 34th Annual SmallSat Conference and will be useful to not only DARPA and OneWeb, but other mega-constellation architects worldwide as well. I am currently looking to expand my initial work to include more hybrid constellation designs, like those being implemented by Telesat, SpaceX, and Viasat. The current development of optical intersatellite links is tedious, but I think that due to public-private partnerships like DARPA's Blackjack program, the future is looking bright. Thank you so much for your time.
Hello, I am Elizabeth Barrios, a PhD candidate in Material Science and Engineering at the University of Central Florida, and a Materials and Process Engineering intern at NASA's Kennedy Space Center. As a PhD candidate working on materials for the aerospace industry, research into developing new materials for existing applications relies on the presence of public-private partnerships. These types of partnerships enable success in challenging current scientific and technological boundaries, success that cannot be achieved by one entity alone. For many years, universities have partnered with large companies or government organizations in order to address very technologically forward, out-of-the-box ideas. This type of partnership allows the student access to tools and expertise that they would not otherwise have access to. It also enables the large company or government organization access to cutting-edge research without any significant loss in time, while also training the up-and-coming workforce. In this way, I have been working on developing new materials for thermoelectric generators through a 4-year partnership with NASA. Thermoelectric generators have been used by the aerospace industry since the very beginning of the space age to provide long-lasting, maintenance-free power to spacecraft by converting heat into electricity. This is a technology that will find continued use in many future missions and will one day be transferred to Earth-based applications as a source of renewable energy. Now, traditional materials used for thermoelectric generators are often constructed of hazardous, expensive, and low-efficiency materials. Future iterations of the thermoelectric generator should be comprised of less hazardous and expensive materials, while also operating at a much higher efficiency. My approach to this problem has been to use easy-to-access polymers, in other words plastics, and modify their properties specifically for these applications. By using university laboratories, along with NASA expertise and analytical equipment, I have begun to show proof of concept thermoelectric performance of these polymer-based materials. This was a concept that was deemed impossible when I first began this work. In this way, I have been able to conduct very exploratory research while also supporting the overall future mission goals of NASA. This type of public-private partnerships allows anyone the chance to take part in pushing the aerospace industry forward through fundamental research. This dynamic, fast-paced environment is the key towards keeping the next generation of aerospace professionals engaged and motivated in the community.
We are living in a time where we witness an international rush to the moon. The advancement in technology and the discovery of water made the moon the priority destination. However, the vast majority of world population are still left behind, and they are not part of the moon rush. I believe going to the moon should be for the mutual benefit of humanity. Involving new players will distribute risk, funds, and benefits. Everyone agrees that going to the moon should be an international effort, but nobody knows how or what this partnership will look like. There are many legal and moral discussions that require the involvement of entities from emerging space countries and non-spacefaring countries. In other words, everyone should be involved. Let's not export our problems on Earth to the moon. So the question now, how to involve everyone to the moon rush? The Moon Village participation of emerging space countries is the only program in the world that provides practical steps for the public-private sectors with a focus in the youth in an emerging space country to be part of the moon rush. The aim of the project is to identify opportunities in the Moon Village by creating a roadmap and supporting the youth to implement this roadmap. The Moon Village Association goal is the creation of a permanent global informal forum for stakeholders like governments, industry, academia, and the public interested in the development of the Moon Village. As a young professional in a non-spacefaring country, I see the goal of the Moon Village Association inspiring. The BESC project is practical in the sense that it provides mentorship for the participants in a structured way to come up with their roadmaps. But writing the roadmap is just the beginning. The BESC project is about communicating the roadmap to potential stakeholders. And this is the importance of the public-private partnerships. The participants can be an independent group of young professionals, a private company, or even a part of a space agency. The stakeholders as well can be from the public or private sectors. As seen in the process of communicating the roadmap, it is iterative and might take years until an actual involvement in the Moon Village happens. We have made a first step for a truly international effort toward the moon. Today, we have 14 teams from 14 different countries from around the world working in their roadmaps. We don't stop dreaming, and we want to see all countries from all over the world being part of the moon rush.
My name is Tobias Niederwieser, and I'm currently a research associate at Bioserve Space Technologies within the University of Colorado in Boulder. We here at Bioserve conduct biological research in space because we want to find out the effects of microgravity and deep space radiation on that biology. And we are doing that for both enabling human future space exploration to Moon, Mars, and beyond, but probably the main reason we are doing this is to conduct fundamental science to find new biological processes that improve life here on Earth. And we are doing these biological experiments over a full spectrum, ranging, for example, from characterizing cancer cells, growing artificial human cells like heart cells and kidney cells, growing plants for food production, or testing new osteoporosis treatments on mice. Currently, this happens on board the International Space Station ISS, as this is the only crewed place where we can achieve microgravity for longer than 5 minutes, which usually is a necessity to conduct biological experiments. So already today, we are working in public-private partnerships together with NASA or commercial spaceflight providers like Northrop Grumman or SpaceX, but also here on the ground with research centers or universities, companies, and startups from all around the globe to really use the ISS as a scientific laboratory and help get their experiments into the space environment. So in order to enable this, since the early 2000s, we have outfitted the ISS as a laboratory with our own designed, engineered, and validated devices of fundamental scientific instruments that are usually found here on Earth in terrestrial labs. So for example, operating right now on board the International Space Stations, we have microscopes, freezers, growth chambers, smart incubators, petri dishes, automated facilities, really everything you need to conduct biological experiments. And we have not only delivered, but we have been using these devices continuously now for over 70 missions with over 150 different experiments in partnerships with over 125 different companies. So public-private partnerships are definitely already a reality today. And the ISS has been a great and powerful scientific platform to host all of that. However, conducting biological research in space is hard and expensive, and that is certainly limiting our throughput and our ability to just try things out. It is therefore now on us, the next generation, to not only maintain this opportunity, but increase its effect by diversifying our portfolio of public-private partnerships to new platforms, new destinations, and making space even easier to access and utilize. And all of that for our own collective benefit.